Hello students, welcome back. In this video, I'm going to teach you how to write the cyclized product from the given alkene in acid catalyst. Don't let this mechanism question scare you. It looks tough, but we are going to solve it easily using the right strategy. So let's get started. If you don't know how to predict the mechanism of the reaction, first you gather the information which you already know. What do you know from the reaction conditions is that there is an alkene reacting in presence of an acid, probably a catalyst, and it's undergoing cyclization to form a six-membered ring. What could be the first step? The first step is addition of this electrophile across the double bond. Hydrogen ion is considered as an electrophile because it is an electron deficient species, and alkenes are considered as electron rich species due to the pi bond. The pi bond electrons are loosely held between the carbon atoms. Therefore, the alkene can donate its pi electrons to the incoming electrophile. Hence, we call this as an electrophilic addition reaction. Remember, alkenes tend to undergo electrophilic addition reactions. Aldehydes and ketones undergo nucleophilic addition reaction. There are two double bonds. Let me number this double bond as 1 and this as 2. Where the electrophile should attack, it depends on the electron density. Whichever is more electron rich, that's where the electrophile will attack. Between these two double bonds, double bond numbered as 1 is electron rich because we have two methyl groups here and both of them are electron donating either through inductive effect or hyperconjugation. Hence, this is where the electrophile will attack. With this much information, you can write down the first step of the mechanism. The reactive center is here. The pi electrons are given to the proton. Always the arrows are written in such a way that from donor to acceptor, the arrow is shown like this. What should happen? First, there is a formation of carbocation because when a neutral molecule accepts a positively charged ion, it is going to form a positively charged molecule that is nothing but carbocation, where the carbocation should form either on this carbon or this carbon. So how do you decide? This is based on Markovnikov's addition. Whenever a carbocation is formed, it should be more stable. So when the hydrogen goes to this carbon, the carbocation will be formed on this carbon, which is nothing but a tertiary carbocation. Hence, the pi electrons are given to the electrophile through this carbon. The bond is going to be formed here and the carbocation will be formed here. So we can write that as it is. So there is a bond formation on this carbon and the carbocation will be formed over here. You can see this is a tertiary carbocation which is better stable as compared to secondary. If the hydrogen would have gone to this carbon, we would have got secondary carbocation. That's why the driving force here is a tertiary carbocation is more stable than secondary carbocation. So what is the first driving force? That this double bond is more electron rich as compared to this double bond. The second is the formation of carbocation. So just to make it simple, what I'm going to do is I'm going to number the carbon atoms. Remember, this is not based on the IUPAC nomenclature. This is just to show where the bond formation is happening. So if I number from this carbon, so this will be 1, 2, 3, 4, 5 and 6 because we are supposed to get a six-membered ring. What should happen now? Bond is formed between the sixth carbon and the first carbon so that we are going to get a six-membered ring. And remember, the carbocation is attacked by the electron-rich carbon through pi bonding electrons. Now, what we will do straight away, we will write six-membered ring. Then we will number it. You can number from anywhere. Okay, so I'm going to number from this carbon. So this is 1 and this I'm going to take it as 2, 3, 4, 5, 6. Depending on how you number, based on that you can write the groups. So now on the first position, what do we have? two methyl groups. Second, there are two hydrogens. Same with the third carbon. Fourth, we have a methyl. So write down that also. Now, what happens to the fifth carbon? Earlier it was tetravalent, now it became trivalent because the pi bonding electrons are given to the first carbon. Therefore, you have to write a carbocation here. And then what about the sixth carbon? There is a methyl over here. So, what all position we have methyl? 1, 4 and 6. Then what should happen? You don't have to write the end product. With this itself, you can still predict what is the product. But let's just finish what will be the final product. You have to regenerate the catalyst. How do you do that? By removing the proton from this molecule. So when you remove hydrogen from here as an ion, right? Then what we are going to get? We are going to get a product like this. The position of methyl groups are fixed and there is a double bond like this. Now, check if there is a product like this anywhere in the options. You are supposed to have it 1, 2 and 4. Look at this. 1, 2 and 3 it is. So not correct. So what about here? 1, 2, 3, 4. Yeah, this is the product form. At first position 2 methyl, second position 1 methyl. Between third and fourth carbon there is a double bond. And at fourth position there is a methyl. Just the orientation of the molecule is different, but you can easily make out that these two molecules are exactly same. So here we have only 3 methyl. You can eliminate this option at first itself. What about here? This is also not correct. So what is the correct option? We have option B. So this is how you have to solve the questions based on the mechanisms. You can predict the mechanism based on the reaction conditions and by looking at the options. Hope this is clear to you, and if you still have any confusion with respect to this, comment your doubts in the comment section and don't forget to subscribe the channel and solve the bonus question. Thank you.